Recording in progress.
Good morning.
Good morning.
We've got a good group of people here today. Oh, well, this weekend I caught the cold. It's not as bad as like my kids had it, but I definitely have a little bit of congestion, a little sore throat. It's the first time I've been sick in 18 months, so it kind of stinks. I guess that was the good thing about staying at home. I just didn't get sick at all. Now my kids got sick. I think my youngest, he's on like cold number 4 out of the past 19 months. Maybe even cold number 5. Because, you know, when you're at school, you just bring home the germs. So hopefully I'll be able to last all day today. I mean, like, you know, for the next hour and a half. How are the rest of you doing?
Getting ready for the week.
Doing good.
Good. Well, so we started last week talking about graphs, and what did we leave off with? I don't even remember. I mean, I know we talked about things like different types of graphs. But we didn't really get into some of the graph algorithms. So I think I'll just start you off with a little bit of an introduction. I guess before we do that, any questions?
Last week we ended with trees and traversals.
Oh yeah, that's right. We were talking about how to like evaluate expressions, stages of a compiler. You know that the stages
Yes,
of a compiler,
indeed.
with starting with the source code and going through the what was the first step? Like the lexer and then the parser. That's called a state machine. So your program kind of moves from state to state. It goes into the parsing, the lexing state, and then the parsing state, then the code generation state, optimization state, and then finally comes out the other end. We'll get into state machines here in about a week or so. Yeah, so let me give you this. Oh, hi. Thank you. My lovely wife just brought me some tea. Oh, that's good. That should help. All right. So there's this company out there called StitchFix, and if you haven't heard of them, and I have no like ties to them at all. I just ran across this because you know, I hear about it like on, you know, they're one of those companies that advertises on things like blogs and podcasts. But what they do is they try to hook you up with clothing that they think you'll like. So you start out, you sign up for an account, and then you go through a brief survey where it asks you like your general, what kind of person are you? What are your general likes? It might show you a few styles, and you rank them. And then every month or so, it takes your survey results and tries to find a set of clothing that it thinks you'll like. So some algorithms take over, and these algorithms try to choose some clothing, and then those clothing choices go to a human stylist who's actually going to look at the choices the computer came up with, and then give it either, you know, yay or a nay, and then those clothes get shipped out to you. And then you can then decide whether you want to buy those clothes or you can send them back. And if, regardless of whether you buy them or not, your choice as to which ones you liked and which ones you didn't like goes back into the recommendation engine, so that next month it might make a better choice for you. And so recommendation engines, of course, are used by all sorts of companies, Netflix, Amazon, pretty much any, you know, large shopping type service out there is going to use some kind of recommendation engine in order to figure out what kinds of things you want to watch or want to buy. But the nice thing about StitchFix is they have a whole section of their website devoted to engineering and algorithm blog postings by their own programmers and their own engineers. So you can find out a little bit about how their company works, and also about whether you, I mean, the reason they post this is maybe to attract some talent. So people might read these and then go, oh, I want to work for a company like Stitch Fix, and then you can go and apply there. So if we go here to their algorithms tour up at the top, it gives a brief overview of some of the algorithms that they use at Stitch Fix. And so if we scroll down here, and I, if you watch this later on, you can pause the video and then read some of the text that's scrolling by, but I'll kind of give you my summary of what I've read going through this here. But basically their business model is you've got clothing over here, you've got clients over here, and then you've got these algorithms and stylists in the middle, and their job is to link you up, with clothing and clients. And so in this circle here is all the algorithms that take place in order to do a job of trying to link you up with the clothing that you like. So one of the problems they have is they have clothing scattered around to warehouses around the country. And this is also a problem they have. What I mean by problem, I don't mean like this is a huge like a business issue. This is one of the problems that their algorithm designers have to solve, which is where exactly do you put this clothing? If you have, let's say 1, 2, 3, 4, 5, 6 warehouses scattered around the clothing, which clothings do you put in which warehouses? People over here on the West Coast, particularly people in the South, don't need so much, and this is just like off the top of my head here, don't need so much winter clothes, right? Don't need clothes that are really warm, whereas people up here in the northern part of the United States do need more of that. People in the southern part of the United States also have a different style than people on the East Coast or the West Coast, right? So you want to move clothes around so that the clothes that people are likely to buy, say on the West Coast, are in the West Coast warehouses, and the clothes that people are likely to buy in the north or the east part of the United States are over in those warehouses. So this is a problem of minimizing things like shipping costs and minimizing storage costs. And of course, there's going to be exceptions. You know, someone over here in the West Coast probably does want to buy a warm jacket at some point, and so you're then going to have to move that article of clothing from one warehouse to another warehouse. And that's also a problem they have to solve, is when do you want to do that? Can you predict when that's going to happen so that you can ship those things before the customers order them? So they have problems like, you know, these represent warehouse locations, and then all these small dots here represent their customers. You know, how do you group warehouses with customers so that you kind of minimize shipping costs? And this part of the blog posting or tour talks about their recommendation engine, where you've got people over here, you've got styles over here, and then these numbers here might represent how good of a match that is between this person and this piece of clothing. I'm scrolling through this quickly. You know, if you want to go through this website on your own and read all the text and go through all the little animations they have, it's quite interesting. So again, you can see pictures of graphs here. So they got an article of clothing, you know, clothing she's gone through, and she's pinned images of clothing that she likes, and it goes through this recommendation engine, and then it tries to match them up with actual items of clothing that they have in their inventory, and tries to figure out which one is the best match for that. You've got natural language processing. So someone might type in, one of the things you can do in StitchFix is, rather than just answering a whole bunch of kind of serious survey questions, you can just type some words about the kinds of things you want to wear. And one of the things the algorithms have to do is analyze the words that you typed in and try to figure out, what did you mean by that? And you know, what do you mean by casual outdoor wedding clothes? What's next here? So this is talking about matching up clothes with stylists. Stylists ultimately making the final choice in what gets recommended to you, what gets shipped to you. We've got logistics, which is moving clothes around in their warehouses. Oh, and you got this another problem here. This is called the traveling salesman problem. If you got a person who has been tasked with picking up all the clothes for a particular customer, that person has to make a little route through the warehouse to stop at the various clothing racks and pick up the clothing. What's the best route for that person to take? What's the best route to take that's the shortest so they can get the most amount of work done in a day? Is it also possible that they could pick up along the way clothing for a different order so that they can actually be putting together clothing for multiple clients at the same time? And again, what's the best route for them to take through that warehouse so that they can walk the fewest number of steps and therefore process the most number of orders in a given shift? Okay, so the customer receives their order, they then try on the clothes, they give feedback to StitchFix about what they liked and what they didn't like, and then that influences decisions that are made next time. So it goes through this cycle of, what are we doing here? So request and feedback goes into the recommendation engine, and then that information goes into the warehouses. Warehouses get delivered to the customer. Customer returns some of the items, but maybe not all of them. That goes back into the warehouses. That becomes more feedback, and the cycle just continues over and over and over again. State machines are a huge part of their process. Actually, this diagram we had over here is a state machine because the client or the customer experience goes through a series of stages, and each one of these stages here is a state, and then each one of these lines is a transition between the different states. There's this kind of state machine, which is showing all the idle articles of clothing going through the different stages. Like there's stages of initial warehousing, and then there's stages of being delivered to customers, and stages coming back to the warehouse, and it has to go back onto the racks, and just making sure that none of the states gets depleted of resources entirely. So making sure that resource allocation goes smoothly. So like state 1 here, make sure that enough resources are coming into it, that it never gets completely depleted. Maybe state 2, make sure it doesn't get too full. Right? So all sorts of graph problems here about resource allocation and optimization. This animation is trying to show here's all the clothing arriving from manufacturers, and then it has to be allocated to various warehouses around the country. Some of them get delivered to customers, some of them get returned back, and then clothing has to move around the different warehouses and so forth. And that's the end of that algorithms tour. So another problem they have is, well, let me just go find the blog postings. And one of the problems they have is trying to identify what color clothings are, the articles of clothing. I need to scroll down to find this. Actually, I should just search for color, huh? So this is their problem of, you've got this article of clothing, and when an article of clothing comes in from one of their manufacturers, the first thing they do is they take a picture of it so that they can show it on their website, but also so that their algorithms engines can start working on trying to figure out, what is this article of clothing and what color is it, what size is it. But this particular blog posting is about color. And so if you ask a human, what color is this? Of course, they come up with different answers. Someone might say blue, someone might say teal, turquoise, dark teal, understated teal, medium saturation and brightness, right? So even humans can't come up with a definitive answer about what color something is. So I think what they did was, so this is talking about taking photos of the articles of clothing, and then they turned to Randall Munroe of XKCD fame, and he did a survey of the 949 most common colors, along with names. So they grouped colors into primary colors, secondary colors, tertiary colors, along with some neutrals. And then it came up with a hierarchy of colors. So you've got your purple colors, common colors, design colors, and XKCD colors. So you've got warm purple, medium purple, ugly purple, and purpley. These are all examples of purple colors. we'll just keep going on that. And so I think out here on the outer ring are the actual colors. These are the color families here. And these are the 954 colors in their survey. Okay, so the first thing they have to do is take a color of a garment and basically reduce it down to one of these 954 or 949 possible colors. But a more interesting problem they have is having a computer try to figure out what color a particular garment is. So after they take a picture of a garment, they then have an algorithm go, actually a couple of algorithms go and try to figure out what color it is. And of course you got a problem when a garment is multiple colors. And so they got two different algorithms that looked at this picture. One of them arrived at these three colors. You know what, I guess it's close-ish, right? This is kind of close to this color. This is kind of close to this color. I'm not sure where this one came from. Oh, so this is a big problem for computers is clothing doesn't lie flat. It's got, wrinkles in it, and it has shape, and it has form. And so there are shadows that the computer has to contend with. Now, they could light the clothing so the shadows are completely eliminated, but I think a human would not like to look at a piece of clothing that had no shadows on it at all, because then you couldn't get an idea about like how full the garment is or what the shape of the garment is. So the computer has to contend with these shadows, and I think that's probably where it came up with this color, right? This is like one of these shadowy colors, and it's really hard for the computer to tell, is this a shadow or is this actually part of the design of the clothing? Another algorithm came up with these 5 colors. You know, this is kind of like here, but this one here is also kind of like the shadows. Here, it found this cream color pretty well, and then it found these 2 other colors in here. So this is a really hard problem for them to solve. A human would say, oh, there's only 3 colors in that garment, but, the computer sees more or less. So they had this idea to take a photograph and break it up into these smaller regions, which they called superpixels, where each one of these regions basically has the same color in it. Now, each one of these regions this is kind of like the map coloring problem we did a week or 2 ago, where each one of these regions can be represented as a node or a vertex in a graph, and then you've got its neighbors. So you can turn this picture into a graph, basically. And so they take a picture that might have 60,000 pixels and turn it just into a few hundred superpixel regions. And that makes it a lot easier to analyze the color of a garment. So here's their graph of the garment. But then you've got like other problems where, even though this garment here is just one color, or at least a human would say it's one color, it's kind of hard for the computer to figure out exactly what color it is, right? Because you got some regions that are well lit, some regions that are brighter, some regions that are darker. So what color is that, really? It's hard to tell. Shoes are a problem. You got to teach the computer not to look inside the shoe, because people don't usually consider the inside of the shoe to be the color of the shoe. It's just the outside of the shoe. And then, this is a problem here, this striped garment. How do you contend with that? And then this plaid garment here. What color is that? Well, it's like a whole bunch of colors. Problem is you can't break up this plaid shirt into these superpixels very well. So they've tried some other things, representing the colors in a kind of a 3-dimensional space and then looking for clusters. Anyway, so lots of really interesting problems that their programmers have to work on, and a lot of them can be just reduced down to graph problems. So that's StitchFix, and like I said, I have no ties to them other than it's interesting to see that both their algorithms group and their engineering group put these blogs up there. And let's see, you can get an idea. What am I looking for here? I'm looking for, careers, I think. Is that what I'm looking for? No. I am looking for the picture. They have pictures of their actual, like, algorithms group. Here it is, I think. Yeah, so what I do is I click on algorithms up here at the top, and then you can get a tour of their algorithms group. And it's just this incredibly diverse group of people that do the programming behind StitchFix. And then on their engineering team, engineering are the people that like run the physical infrastructure. So they might be working on the servers, and they might be working on the actual programming of the website versus the algorithms people. And they're also scattered all over the place. Austin, Iowa, Sunnyvale, Austin, Dallas, San Francisco, Atlanta, San Francisco, Los Angeles.
Professor,
Yeah.
how can they afford so many engineers? I mean, that's a lot of salary to pay.
That's a good question. Presumably they're doing a lot of business. I mean,
Yeah, they're a pretty big company. They do a lot.
I mean, the forward-facing side of it is they're a clothing recommendation company, right? But really what they are is a data science company. Clothing just happens to be what they sell. So their job really is to do all that recommendation stuff. And the clothing that they sell really isn't that cheap. I think if you actually buy the clothing that they recommend, you could probably spend $150, $200 on that box for one outfit.
Yeah, they're roughly about a $4 billion company.
That's their revenue?
I think that's their stock or something. I just looked up their net worth real quick.
And if they're a public company, we should be able to find out their actual net worth, not their stock valuation.
Yeah, it says they did about 1.7 billion in 2020.
That's not bad.
Professor, so all the data that they gather and the algorithms, that can be used somewhere else, right? And they could sell it as well.
I imagine so. There might be interesting things in their privacy policy. I'm looking for, here we go, use of your information. Well, from this privacy policy, it doesn't look like they really like sell out your information to other places. They do say that they share it with third-party providers, but they're mostly like to do technical support, marketing, only to provide services. But it doesn't look like they're really in the business of selling your information. So I suppose that could be good. I'm looking at their FAQ, frequently asked questions. I don't see anything in there about selling information. But for a company like this to do over $1 billion of sales every year, more than I thought. Anyway, let's move on to an actual graph algorithm. So this problem here is called minimal spanning tree. And it has all sorts of applications in things like resource management and resource optimization. Here's just one kind of contrived example. So you've got these houses in this little tiny town. And, this town is so small that up until now, there have just been paving stones in between the houses. So people have made these paths that go between the houses. And some of the paths are longer, some of the paths are shorter. But they decided to actually pave the roads, or turn these pathways into actual roads. And so they're trying to decide where to put the pavement between these houses so that they use as little as possible. They're not a very wealthy town. So this path here would cost 5 units of concrete, and this one here would only be 3 units of concrete. And the idea is, how can we connect up all the houses of this town so that every house is reachable from every house? So there's some way to get, so all the houses are basically connected in to our road system, but using as little pavement as possible. So what do you think might be some strategies that we would use to figure out where to put the pavement? Well, one strategy might be, why don't we just pave all the shortest roads first? So we'll do this one, and then this one, and then this one. Those are all the 2s right there. And then once we exhaust all the 2s, maybe we'll just do all the 3s. So we got this one, and 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 this one. And here's also a 3 right there. Right, the bridge doesn't count. Have we finished at that point?
C to B.
C to B. Oh, another 3 right there. Okay. So at this point, are all the houses hooked in? In other words, is there a path at least one path going to each house. And so A is covered, that's good. B is covered, D is covered, H is covered, F is, C is, E, I, G, and J. So it looks like they're all covered. And then if we add up all this, these amounts here, we've got 2 and 3, 3. Actually, I'll just do it by hand. We got 2 plus 3 is 5. This is 8, 11, 13, 15, 18, 22, 25, 27, 30, 33. I think it was 33. So the question is 33 the fewest amount, the least amount of pavement we could do? Well, one thing I see here is that, like house I over here, it seems like if I wanted to get from I to J, I could either go this way or I could go this way. So there's kind of like 2 paths to get to J, and that means that one of those paths is redundant. I don't need one of them. So which of these links should I get rid of? Should I get rid of this one, or this one, or this one? And then over here, like from D to F, I could either go this way or I could go this way. So one of those links is redundant. Should I get rid of this one, or this one, or this one, or this one? Same thing here. To get from C to B, I could either go this way or I could go this way. So which of these should I get rid of? Remember, we wanted to hook up this town so that there is a way, so that every house is hooked into the graph. But it doesn't necessarily mean that every house has a shortest path from it to every other house, just that it's hooked in somehow. So there's a road that goes to the house, but we don't want any redundant roads. We don't want any roads that for which there's like 2 paths to get to a given house. So the problem we have here is that we're sort of resorting to trial and error. First we went through it and we just like paved all the shortest roads, and then we tried to figure out which ones do we not need. And that's kind of like not a great way to solve a problem, trial and error. I mean, it is the way to solve some problems. There are some problems for which trial and error is the only way that we know to solve it, like trying to crack passwords, is trial and error. But minimal spanning tree does have a way to do this such that you can do it fairly quickly. So that's kind of like the holy grail of computing algorithms is there a way to solve this problem without just doing trial and error? So here's how you do it. Let me first erase all these. So I'll just kind of like walk you through it informally, and then I'll show you the formal description of this. So first step is just, since you are going to be eventually including all the houses, and just pick one to start at. It doesn't matter which one you start at, just arbitrarily pick one. So if you're a computer, you might want to pick at the one that has the first number that's in the list. You might start at A, but it really doesn't matter where you start. So let's do A first. So what you do is you look at all of the paths that are leading out of that house. So there's this one, and this one. And you just pick the shortest one. So there's one with 5, one with 3, and one with 4. Pick one with 3 because it's shortest. And then connect them up. So now we have 2 houses that are in our road network. We're going to repeat the process over again, but with one little change. We are now going to look at all of the paths leading out of all of the houses that we have paved so far. So we're not just going to look at the very last one we did. We're going to look at all of the houses that we have paved so far, which means we're going to look at the path leading out of A and C. So here are all the paths that we should consider. These are all the paths coming out of A and C pick the lowest one. And if there's a tie, you can arbitrarily pick one. So it looks like there is a path leading here to B and a path leading to F that are both of weight 3. You can arbitrarily pick one or the other. Maybe I'll pick this one that goes to B. Now repeat that over again. Look at all of the paths coming out of all of the houses that you've paved so far. You can ignore any path that leads to a house that you already paved. So this one here that has 5 leading from A to B, we've already paved both A and B, so we don't have to look at this path. That means we'll look at this one, this one, this one, this one, this one, this one, and this one. Pick the lowest one. And again, if there's a tie, just randomly pick one. Which one do we pick?
The one with 2 from B to F.
B to F, good.
But then we don't need from C to B, right? Could be. Or if you make it just C to F, or oh yeah, never mind, sorry.
Yeah, we could have picked this one, or we could have picked this one. So we randomly picked C to B. Okay, repeat again. Look at all the paths coming out from all the houses that have been paved so far. We don't have to look at a path that leads between houses that have already been paved. So we don't have to look at C to F. Don't have to look at A to B. Pick the lowest one. And if there's a tie, just arbitrarily pick one. So it looks like we either do B to D, or we could do F to H, or we could do F to J. Let's do B to D. Okay, same thing. Look at all the paths coming out of all the houses that have been paved. Pick the lowest one. That's going to be D to H. Okay, all the paths. Nope, here. So it looks like F to J is the lowest one. And then repeat again. So the lowest one will be this one right here. Let's see, we got a 3 here and we've got a 3 here. So it doesn't matter which one we pick. And then there's not much left to do. We're going to have to pick this one that has 2. And there. Now all the houses have been hooked in. And let's see what we got. So if we started here at A, that then went to C, which went to B, and then from B we branched out to F, and then J, and that went to either G or I, and then I went to E, and then over here in B we branched out and went to D, and then H. So we made a tree. There are no cycles anywhere in this graph. And let's see what the total weight is. So A to C was 3, C to B, also 3, B to D is 3, D to H was 2, B to F, 2, F to J, 3. J to G was 2. J to I was 3. And I to E was 2. So we end up with 3 plus 3 plus 3 is 9. Here's 11, 13, 16, 18, 21, 23. And that should be the lowest that you can go. Now, there were a couple of places where we arbitrarily picked one path versus another because they had the same weight. We would have ended up with a different tree, but with the same minimal weight. So this is called, this particular algorithm was invented by a person named Prim. So this is Prim's minimal spanning tree algorithm. And it works pretty fast. There's no trial and error. This algorithm is called a greedy algorithm. A greedy algorithm is one in which the algorithm just looks at its available choices, picks the best one, and then sticks with it. So a greedy algorithm doesn't do what's called backtracking. It doesn't change its mind based upon new information. Once it makes a choice, it sticks with that choice and then moves forward.
Professor?
Yeah?
So it could be like really nice algorithm for Python, in Python, I guess?
Yeah. This is fairly easy to code up in Python. I think next time, on Wednesday, we'll look at an algorithm that does a little backtracking. So shortest path does a little bit of backtracking because it might make one decision about the shortest way to get to a destination and then realize there was actually a shorter way to do it. So it backs up a little bit and then tries a different path. Okay, so this was Prim's minimal spanning tree algorithm by looking at an actual graph. Let's try to look at it, divorce ourselves from the actual picture of the graph, and try to look at just the numbers. So if we represent the graph as a grid, so this is the same graph, it's got all the same weights in it, but like for example, this one here, this 5 here represents the edge from going from B to A. And you can see there's also a corresponding 5 for going from A to B, since this is an undirected graph. So each of the numbers is in here twice. They're actually reflected around the diagonal. And so I'm going to say that the letters here on the left-hand side represent the vertices of the graph that I've already visited, the ones that I've included in the graph. And the ones here on the top are the ones I haven't yet visited. So the ones on the left are the ones I've paved already, and the ones on the top are the ones that remain unpaved. So here's the algorithm. We got a set of visited vertices, and we got a set of unvisited vertices. And then you arbitrarily pick any one vertex to be the initial visited vertex. Now, in our diagram over here, we arbitrarily picked one to start at. We picked at A, or started at A. So that's what we mean. We arbitrarily pick one of them to be our first visited or paved vertex. So let's go ahead and let's pick A. So you look at all the unvisited neighbors of the visited. So here are all the neighbors. Actually, here are all the neighbors, B, D, and E. And you can see that they're the neighbors because they have edges connecting them. So what I'm going to do is I'm going to highlight this row to focus our attention on the edges that are coming out of node A. or vertex A. I'm also going to cross off A going vertically here because we're never going to go back to A. So we're never going to go from A to A, right? So we're going to cross this out because we'll never go back to it. And that's why in the first step here, we initialize the set of unvisited vertices to be all but the starting vertex. So we immediately eliminate that one. Okay, so we consider each of the unvisited neighbors, identify the neighbor with the lowest edge weight. So we look at these three numbers, and we pick the lowest one. So that's this one right here. So we have selected the edge that goes from A to D as being the lowest one. That means we're now going to highlight the row D because this is now included in our visited set, and we're also going to cross out column D because we'll never go back to it. Okay, so every time we make a choice, we're going to highlight one of the rows and we're going to cross out one of the columns. Now look at all the numbers that are highlighted. This corresponds to all the edges coming out of all the paved houses so far. So I've circled, what, 6 of them? Pick the lowest one. And if there's a tie, just pick one at random. So we've got 2 3s. We'll just pick one of them, and we'll pick this one here. Okay, so we're going to highlight B and cross it out. And then look at all the highlighted numbers. Looks like number 2 wins. So we're going to highlight I and cross it out. So we're going to add it to our visited set, but remove it from our unvisited set. So that's why we're highlighting it to add it to our visited set, and then we're crossing it out vertically to remove it from our unvisited set. And then look at all the highlighted numbers. Pick the lowest one. And if there's a tie, just arbitrarily break them. So maybe we'll do that one there. So we're going to, whoops. I did not mean to erase. I meant to highlight. All right, keep repeating. Looks like we got a 2 here, so we'll select that one. So we'll highlight F, cross it out. You know, if you do this in Python, this is relatively easy to do with sets. And so as you add something to a set, you just do a union. And in order to remove something from a set, you just do the subtraction. Okay, we got a few 3s. Here's one, and here's one. And we'll just pick one. Maybe I'll pick this one. Okay, so I just highlighted C and crossed it out. And look at the numbers that are highlighted. This 2 is the smallest one, so pick that. I did it again. Erased it. There we go. Okay, keep repeating. Looks like there's a 3 here. So in addition to using some sets to represent the visited and unvisited vertexes, you also have to incorporate into your data structure the weights, and you also want to incorporate like where each one of these vertices goes. So you got to incorporate not only the edges in there somehow, but also the weights of them. And then come up with a way to be able to search through the graph fairly quickly. So ultimately, when you take a course in algorithm design, it's going to go hand in hand with algorithms and data structures. It's usually why those two things are included in the same course, because if you have a data structure, you're going to want algorithms to be able to work with that data. And oftentimes, you can't make an efficient algorithm unless you figure out how that data is going to be stored. So the way you store the data can have a huge impact on how fast and how efficient the algorithm can work. We could store everything in just arrays, but then searching through an array is laborious because you have to start at the beginning and go to the end. If you had to do that every single time, your algorithm could take a long time, particularly if there's a large amount of data. But if you come up with a good data structure that's efficient to search, efficient to work with the kind of algorithm you're designing, then the algorithm can go much faster. So let's finish this up. Let's see. I think I just did G. So highlight G, cross it out. We only got a few things left. Here, this one, and this one. So it looks like there's a 2. So I'm highlighting E and then crossing it out. So in our algorithm it says, once the unvisited set is empty, and we've crossed everything out, which means we've now completely emptied it out, we are done. So let's see what we ended up with. So we ended up with A going to D with a weight of 3. And then D went to B, also with a weight of 3. B went to C and I. It went to C with a weight of 3 and I with a weight of 2. C went to J with a weight of 2. J didn't go anywhere. I don't see anything on its row here. So let's go back to I. I goes to H with a weight of 3. H goes to F with a weight of 2. F goes to G with a weight of 3. And then G goes to E with a weight of 2. And then E doesn't go anywhere. So this is what our tree looks like. Notice we ended up with a different tree than on the previous page. That's because we made some different decisions about how to break the ties. But let's see if we ended up with the same total weight. 3 plus 3 is 6. This is 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So same weight as before, but just a different tree. Any questions about that?
Yes.
Yeah.
Professor, can this be applicable in pen testing, like hopping from port to port while scanning, or like scanning for like any weaknesses, like exploits?
I can't say no. I haven't heard about it being used for that, but it is definitely used in computer networks. Absolutely. And it's used so spanning tree gets used for two things, typically, two big applications. One is network optimization, and this road thing is a network. It's a network of roads, and we're trying to optimize the amount of pavement used. It's also used for segmenting computer networks into to make sure that there are no redundant links. In fact, I'm going to show you an example of that here in a moment.
Oh, the spanning tree protocol.
Yeah.
That's why it's
Yep.
called that way.
That's why it's called that. So here's like a picture of, this is like a picture of like my house here, right? I have lots of computers and lots of stuff on the internet. So I've got internet service provider with their link coming into my house. It goes into a router. The router is also a Wi-Fi access point. So I've got, laptops and tablets and phones on the router. And then I've got switches around the house with tablets and phones and TVs and computers and printers hooked up. And, in a typical residential network, this forms a tree, right? It comes in here and it's a tree structure. And there's a good reason for that. Because if I were to, let's say, link up these two switches with an extra cable, have you ever tried that? Have you ever tried taking your tree structured network and putting a redundant link in it? Have any of you tried that?
No, what would happen?
Yeah, the question is, what will happen? Well, what happens kind of depends upon how much you spent on the equipment. If you got your typical residential personal computer equipment, these switches and the routers will do one of two things. They'll either freak out and just start passing data around and around and around and around and around. Right? Because the switch here goes like, okay, I need to send data from this computer to, let's say, maybe from this computer to this printer here, right? I see two paths to do it. I can go this way, or I can go this way. And then once the switch receives the data, it goes, I don't know what I should do with it. Maybe I'll send it out both, right? And then this one sends it out this one here. So the data ends up just like going around in circles. The other thing that might happen is the switch might detect that there's a redundant link and just like shut down. Just go, I don't know what to do with this. I'm just going to take myself out of service. Or it may see that one of these links here is generating a lot of traffic, and it may shut down both of them. Right? So these switches are either just going to completely go crazy, or they're going to shut themselves off. But if you spent more on these switches, if you got enterprise-grade switches, ones for businesses, where you might actually have redundant links on purpose, then when you connect up these switches together, they start talking to each other. And they try to figure out, okay, who are your neighbors? And who are your neighbors? And who are your neighbors? And how fast is this link? Is this a 10 megabit, 100 megabit, 1,000 megabit? Is it a gigabit network? And they run the spanning tree algorithm, and they try to figure out, how can we connect all these devices on the network and minimize, in this case, they want to maximize the bandwidth. They want to maximize the speed. So they do things like they measure, times to send data back and forth. They measure the speeds of the links, and they come up with the best way to connect all these devices. And they may decide to, basically disconnect this cable right here. Not physically disconnect it, they just disable the ports, right, the cable's connected to. So now there's no longer any cycles in the tree. And then if at some point, like a rat or something, or a backhoe comes and it cuts this link right here, then they run a minimal spanning tree again, and they bring this link back into operation. So every time a device gets connected into the network, the routers and the switches run the minimal spanning tree algorithm and try to figure out what's the best way to connect all the devices up. And if they detect any cycles, the minimal spanning tree algorithm will automatically get rid of those cycles. Then when a device is connected or reconnected to the network, they run a minimal spanning tree all over again, and again try to figure out the best way to connect up the devices. So every time there's a change to the topology of the network, the minimal spanning tree algorithm is run between all the devices, and it figures out the best way to connect them up. So this is an example of resource optimization, but in this case, they want to maximize the speed or maximize the bandwidth rather than minimizing something. But it's the same type of problem.
I have a question. Would there ever be a circumstance where it would be efficient to use both paths, right? If you had, say, 2 gigabit paths between things and you were sending data, could you like switch it between 2 paths to get the data there quicker?
Again, some enterprise level switches will detect that you've got a redundant one and will do what's called trunking. So they'll turn that redundant path into basically 2 parallel paths that have twice the bandwidth. So
like the application that I'm curious for something like that would be like, if like, could you create a network inside, say, an office building using people's cell phones, where you've got 100 cell phones in the building and it's creating all these redundant links between the phones and using that to transfer data? Would that be?
Yeah, that can be called a mesh network. And they're not typically done with people's cell phones, but there's kind of like you can go out to the store and you can buy mesh networking devices where you've got your central router and then you've got these other devices you scatter around your house. And they can be used to extend the range of your Wi-Fi network. That's really the purpose of them. So instead of having one big, giant, powerful Wi-Fi station at the center of your house, you've got less powerful auxiliary stations scattered around. And these mesh networks are self-organizing. So each one of the devices kind of like listens to see what other stations can I listen to? What other stations can I make contact with? And they internally form a map of the connections between themselves. And they figure out what's the best way to pass data amongst the different access points. So same idea, not done with people's cell phones, but done with little access points scattered around the house. Is that kind of like what you were getting at?
Yeah, absolutely. In fact, I'm looking at a mesh network repeater right now.
So the idea there is, and this is a huge problem, like especially in my neighborhood, is if I just, if I pull down the list of like all the Wi-Fi networks that are near me, there's like 20 of them. And so those are like all my neighbors all around my neighborhood with their routers and access points. And everyone is trying to out-shout everyone else. Imagine trying to go into a room where there's 20 people and they're all trying to be heard. So there's 2 ways to do this. One is everyone can talk really, really loudly, which is what basically everyone around me is trying to do with their Wi-Fi networks. Is they're trying to, everyone's trying to use their phones and their tablets and their TVs around their house, and the signal can't reach because all the other neighbors are also shouting as loud as they can. Of course, we humans can't hear it, but they're in the radio waves. And it's just not really an efficient way to do it, because the other way to manage a room full of 20 people is to tell everyone, okay, everyone speak really softly. You only have to talk to the person next to you, right? You're only talking amongst your immediate neighbors. You're not trying to talk to the person across the room. So just speak quietly and you'll be fine. And so that's the idea of this mesh network, is instead of having one powerful access point in your house trying to reach every corner of the house, you scatter all these little different access points, each of them operating at a lower power, and then they can more effectively share the bandwidth. There's a limited number of channels they can broadcast on. In the G networks, there's 11 channels, and in the N networks, in the 5 gigahertz range, there's a greater number of channels, but still a limit. on how many channels there are. And so if everyone is being packed in and trying to share all the same channels, there's just a lot of interference. And so what happens is you go out to the store and you go, I'm going to buy the most powerful router or most powerful access point I can. But really a better strategy is to buy a less powerful one and scatter more of them around your house. And that's the idea behind these mesh networks. What I've had to do in my house is, since I have my neighbors who are just blasting out their signals, if I the access points I have are like these prosumer. I'm looking over here because I'm looking to see if I have an example of one, but I can't see one. They're like these prosumer devices, so they're not just your cheap Belkin or D-Link ones where you just plug and play them. They have to be configured, but I've got 3 of them in the house. I've got, you know, a central one, and I've got 2 of them scattered around in different parts of the house, and they talk to each other. So they, as you walk around the house with your phone, they pass the signal off to each other. Basically, they're forming kind of like a mesh network. But I lowered the power on them deliberately, and I narrowed the number of channels they can occupy simultaneously. My neighbors over here, what they do, and I'm pointing generally in that direction. I don't know what direction they're in, but they've set the default setting for the router is maximum signal occupying as many channels as possible. I mean, ostensibly that increases the amount of bandwidth it can send and receive at a given time. But what it means is that your neighbors can't transmit and receive on the same channels at the same time. So when I first turned on my routers, I couldn't get, I mean, even though I had like a strong signal, right? You know, you can just measure the signal strength. I couldn't get any data through them because my neighbors were just like obliterating all the channels. So I ended up having to configure my routers or my access points with less power and fewer channels, so I can kind of like squeeze into the little gaps that my neighbors are left behind. It means that my overall throughput is lower, but at least I can send and receive data. Whereas all the rest of my neighbors are like contending with each other, shouting at each other as loud as they possibly can, my routers are like whispering to each other, but at least we can communicate. So no, you know, I don't have like gigabit wireless networking in my house. You know, it's in the range of tens of megabits, but it's enough for the computers to like be able to stream video and do anything where I need a high amount of bandwidth, like the computers that I'm using for teaching the classes. Those are all wired in directly, right? I've got a 16-port Ethernet switch under my desk, and I've filled up like 12 of the ports, right? Because all the stuff I have directly wired in, and it's sort of so that none of those signals are contending with the wireless stuff. There's only like 2 things in my room here that are actually not wired in. It's my the iPad here and like my phone. That's it. Everything else is wired in. Sorry, that was a long description of what you were asking. So it's absolutely true that for these enterprise-grade switches, if you connect up some switches, some links redundantly, and you have to tell them that you've done that, then it will trunk them together and treat them like a link that has twice the capacity. It's also a good way to make redundant links, right? So that if one of these gets cut, you know, like a mouse or something like that, cuts one of them, then the other one can take over. So that's called trunking when you combine them together. So enterprise networks use minimal spanning tree to eliminate redundant links and bring them back into service, or I should say, activate them when other links have been disabled for whatever reason. They get cut accidentally, or someone unplugs it, or network administrator administratively disables a link just by shutting off one of the ports on the switch. Another application for a minimal spanning tree, and this is again kind of a contrived one, is let's say you've got a new housing development and you want to connect in a sewer system to those houses. So it doesn't matter how the houses are connected, they just have to be connected into the sewer system somehow. Of course, you don't want any redundant links, right? You don't want sewers flowing back into someone's house. And you just want to use as little pipe as possible. So this picture here, you know, could, instead of being paving paths, it could be, these are all the possible ways that we could route the pipes. Which ones should we actually do in order to use as little pipe as possible? So really quickly, we'll finish off with this. How can we represent graphs? We can't actually physically draw graphs inside the computer, but how could we represent them inside the computer? And we already saw one of them. We saw the matrix style. Where you've got the a two-dimensional array, basically. And if you've got an undirected graph, then all you have to do is just indicate in this interior of the matrix, like how the various vertices are linked up. So we might say that, let's see, A goes to B, A goes to C, B goes back to A, and it also goes to D. C goes to A, and it also goes to E. D goes to B and C, and E goes to C. I feel like I missed something there. The reason I feel like that is because it should be like symmetric. So I'm missing the one here. C goes to, oh yeah, C goes to D. Right, so there's a 1 there. There we go. And then if you have a directed graph, then the numbers you put inside the matrix are just the weights. And you can also incorporate directional information by not having it be symmetric around the diagonal. So V goes to X with a weight of 3. That takes care of V. W goes to X also with a weight of 3. X goes to Z with a weight of 6. And that takes care of X. And then Y goes to W with a weight of 5, and it goes to V with a weight of 2, and it goes to Z with a weight of 2. And then finally Z goes to Y with a weight of 1. You get the idea. I might have missed one there, but that's the idea. Another way to store information about a graph is called an adjacency list. And so basically it's an array of arrays, or a list, an array of lists, or something like that. Or yeah, it's a two-dimensional structure. So we've got A, B, C, D, and E. And maybe that's in an array. And then each one of these is a pointer to another array or another list of some sort. So it's just showing you here which vertices are adjacent to each one. And I see that I've misdrawn this one here. A goes to B and C. There we go. So it's called an adjacency list because A is adjacent to B, and A is adjacent to C. B is adjacent to A, and is adjacent to D. So it's a list of the vertices that are adjacent to each other. Now for a directed graph and weighted graph, you're going to have to incorporate the weights somehow into this. Let's see, V goes to X with a weight of 3. So this could be like a tuple, a pair. W also goes to X with a weight of 3. X goes to Z with a weight of 6. Y goes to V with a weight of 2, and it goes to W with a weight of 5. And it goes to Z with a weight of 2. And then finally Z goes to Y with a weight of 1. So you just have to incorporate the weight information into it. And then finally, got a set of edges and vertices. Start out by listing all the vertices, and then listing the edges. So we got an edge that goes from A to B, and I'll do these as tuples, from A to C, B to D, C to D, C to E. Almost done here. I think that's it. 1, 2, 3, 4, 5. I might have missed one, but that's the idea. And then for the directed weighted graph, again, you have to incorporate the weight information in with the edges. So we've got Vx3, maybe, and Wx3, Xz6, Yv2, right? Get the idea. So you list out the set of all the vertices, and you list out all the set of edges. And there are probably other ways to represent a graph, but these are kind of like the three main ones that you might see. And the one that you picked just depends upon what kind of algorithm you're running. The nice thing about the matrix or the two-dimensional array is it's very easy to start at a particular vertex and see which ones are adjacent, right? You just scan through this row and you look for the places where there's numbers, right? Again, you scan through there, look for those places where the numbers. So two-dimensional arrays are very easy because most programming languages support two-dimensional arrays natively. The problem with this is there's a lot of wasted space. There's all these gaps in the data, so you end up wasting some space. So the adjacency list is a little bit nicer because it's very compact, but it requires you to have like lists of lists and the idea of pointers. And then sets also require you to have some kind of data structure that incorporates the notion of a set. Also being able to do things like sets of tuples. So easy to do in a language like Python, probably a little bit harder to do in a language like C or Java. It still could be done, just a little more wordy. So again, the data structure you use depends a lot on what algorithm you're running and what kind of runtime you're looking for. Are you looking for fast lookups? Are you looking for a compact representation? Are you looking for something that works natively in your language? You know, that's going to influence your choice. Well, I didn't get much chance to say hi to the people on YouTube. We've got, just a couple people looking who are watching, but we've got Habibul and someone named DYDX and Alexander. That's great. So I think that's it for I had for today. So we talked about a brief introduction to the kinds of algorithms and graphs that get used out in the real world at a website like, or a service like StitchFix. And also we looked at minimal spanning tree, and we looked at ways to represent graphs in a computer. Next time, on Wednesday, we'll look at the shortest path algorithm. What's the best way to get from point A to point B? And you use this algorithm probably every day when you ask your phone, how do I get from where I am now to the place I'm trying to go? And it's just amazing that a website or a service like Google Maps or Apple Maps, which has a giant graph of all the roads and all the streets, basically in the whole world, can find the answer just a fraction of a second. So again, they're using a really fast algorithm. They're not doing trial and error. They're not doing brute force. They're doing something a little smarter, a lot smarter than that. But it's an algorithm that's been around for decades. Yes?
Does it has to do something with the sorting algorithms?
Well, I mean, it's a search in the sense that you're searching for the destination vertex you're trying to go to.
Okay, so it's nothing like binary search or bubble sort, nothing like that.
I think the picture I have in my mind is like dropping a pebble into a puddle or a pond and then watching those ripples go out. So your pebble goes in where you want to start, and then the algorithm ripples outward until it finally reaches the destination. So in a large graph, you can see it start to like branch out to all the neighbors, and then all the neighbors of that, all the neighbors of that. But where the smarts comes in is you obviously don't want to do paths that take you away from the destination. You want to go towards the destination. So you wouldn't consider ones that take you away. And you do a little bit of backtracking. You might end up at a dead end, and you have to back out of that dead end and try a different path. All right, we'll see how that works on Wednesday. And you can probably find lots of animations for that on YouTube, plus some websites that do interactive demonstrations of it. It's pretty neat. All right, that's it for today. Like I said, on Wednesday, we'll visit shortest path, and then we'll basically be done with graphs from a general point of view, and we'll be ready to move on to more specialized types of graphs. Trees, state machines, mealy and more machines, and that'll occupy the rest of our semester. All right.
Okay, thank you. It was great.
Good. I don't see any questions. So have a good day.
Thank you, Professor. Take care.
Thank you, Professor.
Yep, take care. And still got a couple of YouTube people. So thanks for watching. Hope you got something out of it. Like I said, next time we'll do shortest path algorithms, and then we're on to finite state machines. And then there'll be some space left over at the end of the semester, in December sometime. And so we might get a chance to talk about some really cool stuff, like there's quantum computing, there's going more in depth into some of the stuff we talked about in the rest of the semester, like hashing algorithms, cryptography. Gosh, there's all sorts of stuff we could do. We'll get a few weeks of that in December. So I think I'll end it here. Have a good day, and I'll see you later. Bye-bye.